Finally, let's move on to limit computation. I classify this topic in the following fashion. First, we are going to talk about trivial limits. That's not that important, but it's going to be a necessary step toward other, more important types of limits. Next two examples, 0 over 0 type and infinity over infinity types, are very, very important. One-sided limits are not that important, but sometimes they show up. And finally, infinity minus infinity type limits. That's a bit too advanced, so I'm going to leave that to interested students only. Maybe I'm going to write something like that, but if I do, it's going to be an extra credit. Okay, let's move on to trivial limits. What do you mean trivial limit? All you have to do is just plug in the number and then you're through. Kind of like this. Just plug in x equals to 1 and then that's basically it. Of course, you can use limit rules. You can apply limit rules to separate the limit, numerator and denominator, and then use addition rule to separate all the terms, and then use a coefficient rule, and then you use those multiplication rules, and then plug in the later. But then again, come on, this is too complicated, and also the purpose of all those limit rule business was to justify that we can actually plug in. So why don't we just go ahead and plug in? In some cases, if you just plug in, then you get undefined value like this. Plug in x equals to pi, then you're going to get tangent of pi over 2, and then everybody remembers tangent of pi over 2 is undefined, I believe. And for reminder, here's a graph of tangent function. At pi over 2, we have vertical asymptotes, so that doesn't work. And if you're interested, you can track down the graph from the left-hand side and right-hand side, and then find out one-sided limits. But we're going to talk about those a bit later. So at this moment, let's just move on to 0 over 0 type limits. Okay, this is going to be important, and then we're going to consider two types. First, rational function case, when we have polynomial over another polynomial. In this case, the key technique is factorization. Another situation, if you have radicals, in that case, typically you're going to have to consider conjugation. First, if you factor the numerator and denominator, you're going to get something like this. X minus 2 belongs to both numerator and denominator. So what do you have? You have factorization, and then you have cancellation, and what do you have? You have a trivial limit. Plug in x equal to 2, and then you're going to get a number. So factorization works like a charm. Now, let me warn you a little bit about wrong solution, because I see this relatively often. If you drop all those limit notations, then they are not really right, because first equality is okay, because, well, I did nothing more than factorization. Next equality is a bit problematic because it's okay as long as x is not equal to 2, but not in general. Now, this equality is really bad. Left-hand side is a x notation, and right-hand side is a number. They cannot be the same. But I'm afraid I see this kind of notations a lot, and then I usually give heavy penalty like this. Mathematics is all about communication. Just correct answer will count something like 10%, maybe 20% of the total grade. If you punch the calculator into Wolfram Alpha or something, you're going to get the correct answer, no problem. Mathematics is all about how to write and how to communicate, how to think logically and so on. And, well, this kind of thing is actually far more important than just the right answer. Now, what if you do not use equalities at all and then just show this as intermediate steps? That's okay in college algebra level, maybe in pre-calculus, but not anymore. Because mathematics is communication, it's a language, and you have to have a certain grammar. In the language of mathematics, you have to have a verb. Here, the verb is the equation. Equality is a verb. Without a verb, if you simply list the nouns and phrases and prepositions, I, Tarzan, you, Jane, well, I can understand what you mean, but it's hardly any courteous communication method. Not worthy of college credit. Okay, let's move on. Enough digression. Actually, I show this answer prematurely. What if you have radicals, you have 0 over 0 if you plug in h equals 0. In that case, typical thing to do is to multiply the conjugate. We have square root minus something, so change this minus to plus and then multiply like this. Then what do we have? Please remember this factorization formula. A minus b times a plus b equals a squared minus b squared, and that's being used here. If I square the square root, then square root will go away, so the numerator became much simpler. The trade-off is of course the denominator, but that's okay because this is now changed to plus. This factor here is no longer 0. What happens now? After cancellation, the h in numerator and h in denominator will simply cancel out, and what do you have? A trivial limit. Plug in h equals to 0, and then you're going to get the answer. So we just went through two very important tricks for 0 over 0 type limit. One is factorization, and the second is conjugation. Now let's move on to infinity over infinity type limits, and these kind of things are related to horizontal asymptotes if you express those functions graphically. Rational functions have unique horizontal asymptote. They only have one horizontal asymptote, so it's a little bit easier. And then you can do that by two methods. One is by limit rule solution, and that's okay, and this is the way textbook does. So divide everything by highest order term, boop, 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 and then please note that 1 over x squared, all those things go to 0, and if you pass those limits in, you have a bunch of zeros, except for highest order terms. So what you have, 2 over 1, the answer is 2. This is perfect. However, there's a little bit of a shortcut that I like a little bit better. A lot of students like this one better too because it's shorter. Take the highest order terms and then ignore the rest. And what you get? You have much simpler limit, and after simplification, you get a number. This is my favorite analogy. Highest order term, x squared term, or if you have even higher power, that's going to be the highest order term. That's kind of like total amount of water in Pacific Ocean, for example. And how about 3x? That's huge too, but it's like amount of water in River Mississippi, for example. A lot of water is flowing through there, and then compared with 2 gallons or 8 gallons, that's a lot. But compared with ocean water, that's negligible. So what you have, you just have highest order terms, and then you have an answer. Again, please be warned, if you drop limit notations and these things become really terrible. Left hand side and the right hand side are two different functions. This is not equal at all. And we already talked about this equality being problematic. Left hand side is a function, right hand side is a number. No good. So please remember to leave those limit signs and then use correct mathematical grammar. Now let's move on to a little bit tougher problems with radicals flying around. In that case, please remember to take the highest order terms both inside and outside of the square root. This is what I mean. Take the highest order terms from the inside, ignore the rest. Take the highest order terms from the outside, ignore the rest. Take the highest order terms from the outside, take the highest order term from the inside, okay, like this. Then what do we have? We have much simpler limits right over here, and then you can simplify those radicals. What do you have? X to the 4th power becomes just x squared, and then the square root of x squared becomes just x. So doing this cancellation or ignoring a little bit further, then this 3x term will be gone away, and you're going to get just a bunch of x squares, and then what you have? You have a number, square root of 2 minus 1 over 1. Now, I see a lot of mistakes whenever I write this kind of problems, and believe me, I do a lot. A common mistake is kind of like this. This x to the 4th power looks like the highest order term, so ignore this part. Consequently, this part will be gone, that part will be gone, and you're going to get a wrong answer even if you do everything right. Another kind of answers, let's see, a lot of students just completely disregard square roots, and then of course if you do that, then this part will be gone and you're going to get a wrong answer. In some situation, I saw some students just taking the coefficient square root of 2 minus 1 plus 1 and square root of 9 here, and then get over to square root of 2 minus 1 and 1 minus square root of 9, kind of like that. But of course that's going to be incorrect. Please remember to take highest order terms from both inside and outside. Okay, in some cases you have to be extra careful when x is going to negative infinity. This is okay in general for rational functions, but if you have square roots, that's going to be a problem. Two ingredients. X is going to negative infinity, that's number one. Number two is growth order. Square root and then take the square, and then you're going to get first order. That's an odd number. So if you go to negative infinity, that negative sign will stay there. That's going to cause problem. If you have even power, then negative infinity becomes infinity squared or infinity to the 6th power, 8th power, and so on. They all become positive. But this time, negative number will be a problem. What am I talking about? Please remember this step here. After ignoring, after cancellation, here it is. If you just write it as square root of 2 times x, you're going to get a negative quantity here. But this square root should be positive. How do you make a negative number into positive number? By putting extra negative sign. And that's why I highlighted this part with red. And then consequently, what do you have? Square root of 2 times negative x. That's actually going to square root of 2 times positive infinity. So everything is positive. So we end up with this cancellation and this answer. And here's graphical justification. We have two different horizontal asymptotes as we move to the right hand side, positive infinity, or as we move to the left hand side, negative infinity. So if x is going to negative infinity, is going to be a problem. Then one way to anticipate a possible trouble is by plotting with the handheld calculator. And if you see two different limits, be careful. If you have just one horizontal asymptote, okay, you can be a little bit rest easy and then do some easy things. Okay, we have a little bit of time left to do one-sided limits, so let's talk about it very, very briefly. It looks like this is a good problem. As a matter of fact, we saw this before. Early on, we saw an undefined limit without this plus, but this plus is there, so this is one-sided limit. So how do we handle that? In this case, graph plays a huge role. Draw the graph, and tangent of x over 2, so this is a tangent function, so visualize a tangent function here. You can visualize a tangent function in your head even if you don't have graphic aid, because you're expected to know the basic shape of sine, cosine, and tangent function. And now x is going to pi from the positive side. We are doing this case here. So tangent of pi over 2, but approaching from the right hand side. So that's the case. So pi over 2 case here, we have this vertical asymptote and approaching from the right. It's going down. So the numerator will be negative infinity. So negative infinity over some number, you're going to get negative infinity. If you have graphic aid, then you can go directly to the graph of this tangent of x over 2 over x squared plus 1. This is going to be a lot easier, and because you have the graph of that function you're looking for, and then just take the limit, one-sided limit, as x is approaching the pi from the right hand side. Approach pi from the right hand side, you have negative infinity there. So once you have one-sided limit, think about graph. If you have graphic aid, please use it.